So in example 2, we would like to find out what the order of the group U7 plus U10 is. And this is just the first question we are asking ourselves, and we always want to generalize. So we are looking at a specific example, but we would like to generalize. Can we relate the order of U7 plus U10 to the order of U7 and the order of U10? How does this work? Can we generalize this to G1 plus the order of G1 plus G2 in general? And this is like a theme for this section. We would like to learn more about the structure of this new type of group, this external direct product, by looking at specific examples and then seeing if we can generalize and learn something more about the structure of our external direct products. So let's start this problem by remembering what U7 and U10 are. So U7 has elements 1, 2, 3, 4, 5, and 6. So all numbers who are relatively prime with 7, mod 7. And similarly, U10, units mod 10, it's 1, 3, 7, and 9. And the problem is suggesting to complete the table on the right. So here we have 3 elements that are in U7, 6, 2, and 3 over here. And then we have 3 elements in U10. Well, actually 2, 9, 9, and 3. And we are looking at, we want to write down the order of A, the order of B, and then figure out the order of A, comma B. And so the order of A and B, we have computed those before, and you can convince yourself that this is true, or you can look it up, but the order of 6 in U7 is 2, and the order of 9 in U10 is also 2, and the order of 2 in U7 is 3, the order of 9, well, still 2, the order of 3 in U7 is 6, and the order of 3 in U10 is 4. So this is something that we already know how to compute, so here we are. Let me do a little bit of cleanup. Next, we just brute force are going to compute the order of our ordered pairs. So 6, 9, what's the order? Well, yeah, let's multiply it by itself. That is 36 mod 7, since the first computation happens in U7, and then 9 times 9, that's 81, but we are going mod 10. And that is 1, 1. So that's the identity in U7 plus U7. So this tells us that the order of 6, 9 is 2, since I only had to multiply 6, 9 by itself, so square it to get the identity. So we can fill in the order of A, B in our external direct product is 2 for 6, 9. All right, next one. You may want to pause the video and do the work yourself, and then you can compare with my work. So let's just brute force compute our powers. So when I'm starting with powers of 2, 9, I get 2, 9. If I square, I get 4, 1. If I cube, I get 1, 9. If I take it to the 4th power, I get 2, 1. That's to the 4th power. If I'm going to the 5th power, I have 2 times 2, that's 4 again. I have 1 times 9, that is 9. That was the 5th power. Still don't have 1, 1. I'm doing this until I get 1, 1. I have 2, 9 to the 6, that is finally 1. 2 times 4 is 8, mod 7 is 1, and then 9 times 9, 81 mod 9, that is 1 finally. Okay, so we found that the order of 2, 9 is 6. Okay, let me fill that in over here. So I get 6. And the last entry was 3, 3. So that is 3, 3. If I square, I get 2, 9. If I cube, I get 6, 7. And if this is too fast for you, just pause and convince yourself that my computations are correct. That's never a bad idea. It's 4, 1. If I take it 3, 3 to the 5th power, I have 5, 3. If I take it to the 6th power, I get 1, 9. So I finally have a 1. This is getting a little bit old, so could we maybe predict what this is going to be? Let's look at the pattern that we found when we computed powers of 2, 9. So how long did it take us to get 1s? Well, for the second entry, we got 1 almost right away. So 9 squared was 1. But unfortunately, 2 squared wasn't. But 2 cubed was 1. And so we can kind of see every second entry gives us a 1 in the second coordinate, and every third entry, 1, 2, 3, 1, 2, 3, gives us an entry, a 1 in the first entry. So we needed a multiple of 2 and a multiple of 3 to come up with 6 as our order. And if we're going over to the right here and looking at 3, 3, in the second coordinate, it took the power of 4 to get a 1. In the first coordinate, it took a power of 6 to get a 1. So every fourth entry, I will get a 1 in the second coordinate, and every sixth entry, I'm going to get a 1 in the first coordinate. So when are we going to get a 1 and a 1? What does our power have to be? Well, it has to be a multiple of 4 and a multiple of 6, and 12 is the first one that's going to work. So, do you see the pattern right here? So, in order for an element a comma b to the n to be the identity, our power n must be a multiple of both the order of a and the order of b. And this is going to lead to our first theorem. So we need a multiple of the order of a and the order of b, and we want the first multiple that works. We have a name for that. That's called the least common multiple. And that is what Theorem 8.1 is going to say. So if we have groups G1 through Gn of finite order, and we have an element G1, G2 through Gn in our external direct product group, then the order of this element is going to be the least common multiple of the individual orders. So the order of G1, order of G2, and so on, all the way to the order of Gn. So that is our first theorem that comes pretty directly out of just looking at one example.